pure form. And we gave an example of copper. The ore is called chalcopyrite, which is copper iron sulfide. And we say there are other ores like copper sulfide. And as we said that before we start the refining process, we normally concentrate the ore. To concentrate the ore means you want to start with a material which contains as much as your final product as possible. And we talked about a number of processes, flotation. We talked about you can do hand picking, you can do a hydraulic process where you mix the mixture with water, and then you run it through a slopy surface with some pores. So we said the heavier particles will move slowly, the lighter ones will move fast. So you can be able to separate them by gravity. So for copper, we said that the ore is copper sulfide, and we cannot get it directly from this. So what we normally do is to heat the ore with silicon dioxide and oxygen. When we do this, a reduction process occurs. So we get copper 2 sulfide, iron silicate, and sulfur dioxide as a waste. And then we said that you can be able to separate. This one is a gas, this one is heavier, so it will settle at the bottom, and then you can now get your copper sulfide by, you can take your copper sulfide and heat it in presence of oxygen to convert it to sulfur dioxide again and copper. And we say this end product is normally not very strong. It's called a blister copper. It's called a blister copper, and it's called blister because it's very brittle. And in terms of purity, it contains about 98 to 99% copper. Now, during the extraction, we said our aim is to get copper from the sulfide. We talked about stages, and after you have done the extraction, there is the process of concentration. But what we need to apply to know that is after you have done after you have extracted copper, you can dissolve it in sulfuric acid to form copper sulfate, and then you purify this through electrolysis. So we said you can do electrolysis, and in the electrolysis you say you take copper sulfate solution, which you have formed by dissolving your copper sulfate in sulfuric acid, and then you put it in 2 electrodes. The impure copper which you have extracted will form the anode, and the pure cathode will form the pure copper will form the cathode. So we said at the cathode, we start with the anode. At the anode, what will happen is that the copper, which is here, will dissolve with solution. The copper will dissolve. At the anode, the copper will dissolve. So copper will dissolve from here, as you have seen here now, copper dissolving into solution, and then the copper which has dissolved into solution will move to the cathode and get deposited. So these ions will move to the cathode and get deposited. So by that, you'll be able to purify your sample. And we said the impurities contain some metals which can still be used for other processes. So the uses of copper, we said in electrical wires because of good conductivity. It can also be used in plumbing. And then we also talked about in boilers, heat exchangers, because again, it's a good conductor of heat. And in some countries, it's used to make, it's a coinage metal. And then copper can also form alloys, copper and zinc, they form brass. We also talked about when you mix copper and tin, you can get what we call bronze. And then we talked about titanium. I'm just running through this. We say this is a very expensive metal because of the process of getting it. It's very light. It is used in aeroplane, and because of its compatibility with the body, with the physiological processes in the body, it has found use in medical field to replace hips. So I think you have heard about people who have gone to do what we call hip replacement, where the natural hip is removed and replaced with metallic ones. Titanium has been chosen because it's friendly, and it's also used for making pipes in chemical industry, where corrosion is likely to occur. So for the titanium, it is not very expensive. No, it's quite expensive. And we said you cannot reduce it by using carbon or any carbon compound because it forms carbon carbide. It forms carbon carbide. And then we also said you cannot again reduce this carbon carbide by reacting with chlorine, because the problem is the product that you form will be very highly it will be very high. It's very high. It's not very stable. It doesn't want water. So to reduce this, you need to carry out this reaction at high temperature and use metals to reduce the product. So for the extraction, we looked at the process. So we said when you convert that, you convert it to titanium chloride plus carbon monoxide, which is a gas which will escape. Now to reduce this, we said you can't use carbon. Now you can reduce it either with sodium metal to form titanium and sodium chloride, which you can just remove by dissolving in water. So the sodium chloride will dissolve and the titanium will remain. And then for the reduction, you can also use magnesium, because it's a highly reactive metal. So the magnesium again can displace titanium to form titanium plus magnesium chloride. Then I think you want to look at iron. So iron is normally extracted from using what we call a blast furnace. Those of us who teach chemistry in high school, I think this is something that is done in high school. It's a process. So it's called a blast furnace. So the common ore for iron, it is called hematite. So hematite is a mixture of iron 2 chloride, no, iron 3 oxide and iron 1 oxide. So it's normally you get this. So this is the ore that you get when you mix that. You can have one of these. So you can either use the oxide or you can use this compound here. And so in the extraction process, remember we talked about the blast furnace, where you introduce your ore, your raw material. So the raw material is the ore, coke, which is carbon, and calcium carbonate. We shall see what calcium carbonate does. And then down here, you introduce the hot air. So hot air is introduced down here for the purpose of increasing the temperature of the furnace. And then this furnace is made of steel, which is heat resistant. So you can see with the furnace that as you go up, the temperature reduces. So the highest temperature is at the bottom, but as you go up, it reduces. And then once you have formed your product, there's also some waste gases which will be released up here. So waste gases will be released, and then you are going to get your product down there. So the product will be formed either as molten slag or molten iron. So iron is denser, so it will normally stay at the top, and then the slag will be up here. So in terms of the processes, so the heat, we said air is blown from the bottom, hot air, very high temperature, to increase the temperature of the furnace, and it is heated using waste gases which come from the top. So you can see recycling, so that we save on energy. So we heat that, and then we generate hot air, which is used to carry out the reaction. Now, what we have is coke. When you talk about coke, coke is carbon. So we said you introduce iron oxide, coke, and limestone. So what happens is that carbon, which is coke, will combine with oxygen to form carbon dioxide. And as the temperature increases, the carbon dioxide will combine with more carbon to form carbon monoxide, which is also a reducing agent for the process. So the carbon monoxide which is formed will react with our raw material, which is iron 2 oxide, and it will reduce it to form iron plus carbon dioxide. Iron plus carbon dioxide. So in the hotter part of the furnace, the carbon will itself act as a reducing agent. And notice that if not at this temperature, the other products of the reaction will be carbon monoxide. So this is what we are saying. So when you have this happening, you can also get carbon monoxide as a product. So at high temperature, we say carbon can act as a reducing agent in itself, but at low temperature, carbon monoxide is a better reducing agent, so you can use that one. So the temperature of the furnace is hot enough to melt iron at the bottom, which will flow down the bottom where it can be tapped off. So we are saying here the temperature is so high, 1800. At this temperature, whatever comes here will be molten. And because it's molten and there are different densities, iron will settle down, and then you'll have molten slag at the top there. And then we have limestone, which is calcium carbonate. Why do we introduce calcium carbonate? So the calcium carbonate is introduced because of two functions. One of them, when it is heated, it produces carbon dioxide. And we have seen that this carbon dioxide is the one that will react with carbon to form carbon monoxide, which is also another reducing agent. And then from the same limestone, when you get calcium oxide, this calcium oxide will react with silica to form calcium silicate. So calcium oxide will react with silica to form calcium silicate, and this silicate is a slag. It's a very hard material which is used to make rods. So it's normally used to make rods. So you can see that this process, so that's just a summary of the process. So you have that, and in the process you get your product. So we'll see how this one happens. So that is just a summary of the process. So the waste product here, in this process, we can say the waste product is carbon dioxide and carbon monoxide. We talked about these pollutants during the introductory part. And then we said, so you get different types of ions, and the difference in these ions will depend on the percentage of carbon in the ion. So we have the cast ion. So this is the one that is normally gotten from the process. The molten ion, which is obtained from the bottom of the blast furnace, and this ion is not very smooth, and therefore it is normally used for making a casting. It's not, and also it's not very pure, so it contains about 4% carbon, so very little amount of carbon, and this carbon makes it to be very hard and also very brittle. That means it's easy to break, and it tends to break rather than bending. When you try to bend it, it breaks rather than bending. So the cast iron is used to make things like manhole covers, the guttering, the drainage pipes, the gas blocks, and so on and so forth, where bending is not needed. So it's used to make flat surface. And then we have the steel iron. So most of the iron is used to make a number of types of seals. So these steels are called steel because they are a family of alloys which are made by mixing iron and carbon. So we mix, when you increase the number of iron carbon percentage in the ion, you make it to be a bit shiny and even strong. So still you have heard about stainless steel and so on and so forth. So the impurities in this form of ion from the blast funnel will include carbon, sulfur, phosphorus, and so on and so forth. And this one can now be removed, and we increase the number of carbon. So how do we remove sulfur from the product? So to remove sulfur, we just separate. So sulfur is removed by reacting the product with magnesium. Magnesium will pick up a carbon. Magnesium will pick sulfur to form magnesium sulfide. And then the other impurities can still be removed if it is still impure. We saw carbon can be removed further by reacting with oxygen to form carbon monoxide, and this can go as a gas to leave the ion. So for this type of ion, steel ion is normally purified. So it is, as mentioned above, it is a pure form of ion, and it is used to make many things. So we have different types. Again, we have what we call a roughed ion. So if all the carbons is removed from the ion to give a high purity ion, then this ion is called a roughed ion. And then you can have another one which contains some percentage of carbon, smaller than what we started with, about 0.2%. This one is called mild ion. And so for special needs, I've said we use special steel, and this special steel contains high percentage of carbon. I'm just trying to summarize because of so that you can be able to get the other point. So you can be able to summarize that. And we have different types of ions. You can see that you can still mix iron with other compound metals like chromium, nickel, and get materials which are special resistance. So for cookeries, cutlery, and utensils, it can also be mixed with titanium to form materials which can withstand high temperature, like the gas turbines and spacecraft. It can be mixed with manganese to form, again, very hard material. So this one is used in rock breaking machineries, the ones which are normally hit the rock so that it can break in small pieces. And also some railway tracks also contain this material. So the advantage that we use here, it is because of the hardness of iron. So those are the types and uses of the iron. So the problem associated with mining of this material, so when you talk about the process here, we look at landscape. We said we normally, because extraction means you dig the land, interfere with the landscape to get the raw material which you then process. So we have a lot of loss of the landscape during the process of extraction and also transportation. We have noise pollution, and then you have air pollution because of carbon dioxide which is produced. So this carbon dioxide causes what we call greenhouse effect. The carbon dioxide also causes what we call acid rain during the extraction. And then so we are talking about landscape, noise, atmospheric pollution because of the gases. We have sulfur, we'll get some sulfur dioxide, we'll get carbon dioxide, greenhouse gases, and then we have carbon monoxide, which is poisonous. And then we have also slag. When we get too much of it, it becomes a problem to dispose. So how can we reduce the problem? So to reduce the problem, we said one of the solutions is to recycle. When you recycle, the process is cheaper than getting the material from its raw state. And then we have also said that when you do recycling, you save energy. So there's a lot of energy saved during the process. And then, notwithstanding, we said that recycling will also be cheaper because it will not use the same process as the original process. So the solution here is recycling. You can decide to recycle the product instead of getting it from the raw material. We can also talk about another metal. It is called tungsten. So this one is also a very useful material. It normally exists as, the symbol is W. So it normally exists as tungsten 6, WO3. And it is a material which is of use. Normally, because of its reactivity, it cannot react with you cannot reduce it using carbon, because what happens is you form tungsten carbide. Just like titanium, you get titanium carbide. So we avoid using carbide to reduce. So to reduce tungsten, we reduce using hydrogen. So we use hydrogen to reduce tungsten. So tungsten oxide plus hydrogen, you get tungsten plus water. And of course, the excess hydrogen can be carried away and be used for other materials like the Haber process. So this is what you get from the process. So you have, so that is tungsten. And then we can look at another one here, another metal of interest, which is aluminium. So aluminium normally exists as bauxite. Bauxite is aluminium oxide hydrated. Aluminium oxide hydrated. So for the aluminium, just give me 1 minute, I lock the door. I'm in an office and it's not very safe. Just a minute. Okay, sorry, sorry about that. So I think we can look at we were talking about iron. No, aluminium. So aluminium is gotten from the oxide, and the oxide is aluminium oxide with water. It is a very reactive metal, very high in the electrochemical series, and therefore it cannot be extracted by using carbon reduction. So the temperature needed for this process will be too high to catalyze, so it's not economical. So instead of using reduction for iron, we normally do electrolysis. So to do electrolysis, the ore is first converted to what we call iron oxide. through a process called the Bayer process. And then after this, electrolysis is then carried out in this solution, a compound called cryolite, which you are going to see shortly. So in short, what we are saying, you cannot reduce this, it's very reactive. So what you need to do is to carry out electrolysis, but before you carry out electrolysis, you have to convert it into a compound which can be easily electrolyzed. So the iron ore that we use, we say it is called bauxite, aluminium. No, they're not iron, aluminium. It's Al2O3. And this bauxite contains impure ore. So you need to purify. So to purify it, we use what we call the Bayer process. Bayer process. So this process involves crushing the product. So you crush the product, breaking into small particles for easy reaction, and then you react it with the sodium hydroxide. We know aluminium oxide is amphoteric, so because of this, it can react with both acids and bases. So we react aluminium oxide with sodium hydroxide in presence of water. What you get is aluminium oxide. Now what you get is sodium aluminium hydroxide. It's called sodium aluminate. It's called aluminate. It forms a complex. So you get a compound where aluminium is, so here you get a complex where aluminium, as instead of aluminium hydroxide, you add another hydroxide to have 4. So aluminium can have 4 because it has got what we call an empty orbital to form the compound, and then the extra charge is neutralized by using sodium hydroxide. So you get aluminium, sodium aluminate as an impurity, and this impurity is soluble in water, so you can just dissolve in water and filter to get the solution. And then now the solution is heated. This one again is heated at very high temperature. When you heat it at very high temperature, it breaks down to form aluminium oxide aluminium hydroxide plus sodium hydroxide. So it breaks down to the starting material. So aluminium hydroxide plus sodium hydroxide. And then again, what happens is that during the process, because we know solids don't conduct electricity, what will happen is that this compound is heated to very high temperatures between 11,000 to 12,000, not 1100 to 1200 degrees Celsius. When it is heated at this high temperature, it will break down to form aluminium oxide and water. So this compound here is the one that we normally use to do electrolysis, aluminium oxide. But because we know that the temperature of this compound is very high, during electrolysis, what is normally done is that this compound, aluminium oxide, is mixed with sodium aluminium fluoride, what we call cryolite. So it is mixed so that the melting temperature can reduce. So it is mixed so that the melting temperature can reduce. So we have, so this is what we have. And when you mix this aluminium oxide plus cryolite, then you now carry out electrolysis. So in this is the setup for electrolysis. You have, it is put in a chamber which can withstand high temperature, and in the chamber it is coated with carbon. It is coated with carbon, which acts as the cathode. And then there is also a series of anodes which are connected together. So we use carbon. So we use carbon electrode The solution that we put here is aluminum oxide plus cryolite. And cryolite is added to reduce the boiling point, the melting point of aluminum oxide, because you cannot do electrolysis of aluminum. It has to be in a liquid state. So when you melt, it means you heat at high temperature, and therefore to reduce the temperature, you need to mix it with some impurities. So this is the setup of electrolysis. The carbon is the anode, and then the cathode is the surface coated. So although the cell is labeled as cathode, the lining is not labeled as cathode, the effective cathode is the mainly the aluminum that forms at the bottom of the cell. So we have that. So I think the process is shown here. So molten aluminum will normally be gotten out of this through a tap, and then others will form. So aluminum forms here. So how does it form on the coat? So you have to understand the process of electrolysis. So when aluminum oxide ionizes, it produces aluminum ion and oxide ion. The aluminum ion, because it is plus, it will go to the cathode. So anything which is plus goes to the cathode, which is negatively charged. So aluminum will go to the cathode, and when it goes to the cathode, it will receive an electron and form aluminum solid. So what we are saying here, aluminum will gain electron and form aluminum oxide, which will coat, and form aluminum. So aluminum ion will form aluminum, which will get deposited on the side of the vessel. Now the oxygen, because it is positively charged, this oxygen here, it will move to the anode. Anything which is negative, the oxygen, because it's negatively charged, it goes to the anode, which is positively charged. So these three here, so the three that I'm trying to find out here, these are the anode, the positive electrode. And then the negative electrode are also carbon. So aluminum will get deposited here, because once it reduces to form aluminum, the metal will get deposited on the surface. And then the oxygen will go to the anode, where it will be reduced to oxygen gas. So this is just a reduction process. You remove the 4 electrons, and in the process you generate oxygen gas. So what happens is that we'll see that during the process, when you generate oxygen gas and the temperature is very high, the oxygen will react with graphite or carbon to form carbon dioxide. So during the process, the electrons will be eaten out, and in the process they produce carbon dioxide, and you'll continuously need to replace the electrodes. So these ones are replaced because when you form oxygen in plus carbon at high temperature, the oxygen will combine with carbon to form carbon dioxide. So we need to replace the electrodes continuously. So that's a major expensive process. So the continual replacement of the anode is a major process. And also we know that when this reaction occurs, then we also produce carbon dioxide and also some carbon monoxide in presence of less amount of carbon. And what we see here is what to consider. We have talked about the same process, that to produce aluminum, you need 3 electrons. So that means high amount of electricity. So it's quite expensive to produce this material. And also to replace the anodes during the process. And also one of the materials that is used, the cryolite, the sodium aluminum fluoride, is expensive. And then we have problems associated with the environment, during the process extraction. So just like the other one, we talked about loss of landscape, noise, and also noise and also pollution. So there is noise pollution, there is global warming because of producing carbon dioxide. And then we have said that there is also a loss of landscape, noise, and then production of carbon dioxide. So these are things that we need to consider during the extraction. So the same process, greenhouse effect, poisoning, fluorine compounds are also formed. We know fluorine, we said it affects the ozone. That's what we said from the other process. So we need to think about other processes. So the solution to this is just recycling. So you just recycle. So what are some of the uses of aluminium? So aluminium is usually used as an alloy with other metals such as silicon, copper, magnesium, because pure aluminium is very light. So to get a compound of aluminium which is friendly, we normally try to mix it with other compounds or other elements to form alloys. So we need to know what to mix with so that we get the correct compound. So aluminium, I think some of the uses we know. We'll not go word by word, but we know the major one is the major use of aluminium is making utensils, parts of the aeroplane because it's light. And we say this is done because of the lightness, and then to make pans because it conducts electricity easily. Sorry, I went to something else. So it conducts electricity easily, and so you get that, and then so you talked about electricity and also good appearance. So there is a process which is called anodizing aluminium, where you use aluminium as the anode. When you use it as the anode, it will dissolve in water, in the solution, and then get deposited on the other material. So this is just like coating with aluminium. So the uses are indicated on this table. So it is used to make aeroplane because it is light. It is also used to make superstructures in body vehicles, tubes, because it's strong and light at the same time, and resistance to corrosion. Sometimes it's also used to make power cables because it conducts electricity and it does not undergo corrosion easily. And then we have now the other metal that we can talk about is zinc. Now for zinc, we know is an important metal. It is normally extracted from zinc sulfide, what we refer to zinc blende. Zinc blende is zinc sulfide, or sometimes it can be gotten from a zinc carbonate. It can sometimes be extracted from zinc carbonate, but the most important one is zinc blende, which is just zinc sulfide, or you can get it from calamine, which is zinc carbonate. So in all this for zinc, the process starts by what we remember we talked about roasting of a metal. Roasting, we said you heat it in presence of air to get products of need. So you can do this, and when you heat this, you get zinc oxide plus sulfur dioxide. Sulfur dioxide is a waste material. You can use it for making sulfuric acid, and then the zinc oxide you can apply it for other use. So the same process, you can also get this from zinc carbonate. And then once you have gotten the zinc oxide, you can now reduce it just like we saw in the blast furnace. You can react zinc with oxygen, carbon can react with oxygen to form carbon dioxide, and then the carbon dioxide can react with carbon to form carbon monoxide. And then these are the products that can now reduce your oxide into the metal. So you can see zinc oxide reacts with carbon monoxide to form zinc plus carbon dioxide. The zinc is also reduced by carbon to form the zinc. So it can be reduced by that. And what happens here is that this is just like in the blast furnace. In the blast furnace, you just reduce. So there's a lot of information here, but we are just reducing zinc oxide by using carbon or carbon monoxide to give you the metal. So you get that. So I think here they are just trying to explain that the process is reduction because zinc oxide is converted to zinc. So reduction means you're removing oxygen. You are moving from zinc +2 to zinc +0. So oxidation state has reduced, and so on and so forth. So that's how we get it. And we'll see that this metal can also be purified further. If you want to purify, you can even use distillation by heating the product at different temperature and correcting the vapor. So what is the importance of zinc? So again, it's used to make alloys. Zinc is also used as a pigment, especially for motor vehicles. You have seen people spraying their vehicles with vapor, white vapor, that is normally zinc. And then they cover it with other things. And then zinc oxide is also used in rubber to prevent it from UV radiation. So making of tires, so they contain some zinc and also some cadmium. Zinc chloride is also used on lumber to make it fire redundant and also as a preservative. And then the oxide is also, the sulfide is also used because it produces, when light shines on it, it produces color. Sometimes it's used as a luminescent paint on clock surface, so that when light shines on it, it can produce some colors. And then zinc sulfide is also used as a fungicide to kill fungi. And the zinc itself as a metal is also used as a supplement. Inatumika kama supplement. So I think maybe that's what we should cover under zinc. And then this just shows the process of cleaning. Again, you can just do like copper. You can dissolve it in sulfuric acid to form zinc sulfate, and then you carry out electrolysis using zinc oxide. No, using zinc electrodes. So you can use pure zinc, and then to be the cathode, not to be the cathode, and then the impure zinc to be the anode. So the impure zinc will dissolve in solution, and once it dissolves in solution, it will get deposited on the cathode as zinc. So this is what we get over here, and then it has also other industrial use, which I think we have mentioned before. So I think here we can just focus on the uses of zinc. The other metal which has been used before is lead, but the usage is being minimized because it has been found to be poisonous. So lead exists as lead sulfide, and also lead carbonate, what we refer to as cerussite. And again, for the conversion purposes, the lead, they are heated in oxygen to form lead oxide. So heated in oxide, so galena, which is lead sulfide, or the carbonate, which is cerussite, they are heated in oxygen to form the metal oxides. And then these metal oxides can now be reduced. They can now be reduced. So the lead, because it's less reactive, is normally reduced by using carbon. So we don't need to pass it through the blast furnace. Just carbon will be enough to reduce the lead and form it to form lead oxide. So this is how we reduce lead and give us our product. So the major use of this lead, it is used in the blast, not in the blast furnace, in the battery industry. So we still have the car vehicles, the lead batteries. Lead is one of the electrodes for the formation of that. So that is for the metal. There is something that we can look at here. Let's talk about so we have some two processes here, which we can just look at quickly, maybe 2 minutes. Let's see. So I think there's a process called, you can see we are falling out. Let's just look at this briefly. There are two important raw material. We have got what we call ammonia, which is used in the fertilizer industry. So ammonia is normally made from a process called Haber process. And in the Haber process, we combine nitrogen from the air and hydrogen, which we get from natural gas, what we refer to as methane. So when you combine nitrogen and hydrogen, you get ammonia. You get ammonia, and the scheme is shown here. So you have nitrogen from the air, hydrogen from natural gas. So these ones are mixed, and when they are mixed, they form ammonia. So this reaction is carried out at high temperature, 400, at temperature 400 to 500 degrees, which we consider low temperature here. So the temperature is 400 to 450. The pressure for this process is high because of what goes here according to Lachetla's principle. This reaction, because you are forming fewer gases than you started with, it means that it occurs with reduction in pressure, so you need to carry it out at higher temperature. And at high pressure, and then we normally use a catalyst. So the catalyst that we used in this process is called iron. So we use iron to catalyze this reaction. So when the two mix, you can get your aluminum. You can get your ammonia, which you can cool to get liquid ammonia, and then any excess hydrogen. So here gases, so the gases are mixed in the ratio 1 to 3 by volume, but in case you have any unreacted gases, they can be recycled to form the product. So the catalyst is just used to speed up the reaction, and the catalyst is iron. Normally we add sodium hydroxide as a promoter to make it more effective. And then pressure. So the pressure, we said the reaction requires high pressure. So the reaction requires high pressure, and the temperature that we use is fairly low. So, and then we talk about importance of checking the environment. We normally recycle the products. So the products are normally recycled. So I think just to mention this, the conditions about temperature, we are saying that for those of us who did physical chemistry, we are saying that if a reaction is exothermic, an exothermic reaction will be favored by a low temperature. So for a system which is in equilibrium, if it occurs with loss of heat in form of energy in form of heat, it will normally be favored by low temperature. So in this equilibrium, we are saying that we use 450, and we call this one low because in industrial processes, this temperature is not high. So there are reactions which go up to 2000 degrees, as we saw for the blast furnace. So we say low temperature, because again, we don't want to be very low. When your temperature is very low, the reaction will also be low. So we talk about 450, which is a fairly low temperature. And we have just explained why that is so. It's because the forward reaction is exothermic. So to carry it, you need a fairly low temperature. But you can't use very low temperature because the reaction will be very slow. So we need to compromise between the two. And then for the pressure, we said you use high pressure. Again, not very high pressure, because when you use very high pressure, the process will be expensive because you need very special vessels that can contain high temperature. So we use 200 atmospheres as the temperature, as the pressure, and then for the catalyst we use iron. So these are just there to improve the process. And then we have another process that we can talk about just briefly. I know the numbers have fallen down. So we have what we call contact process. So for the contact process, this one we use to manufacture sulfuric acid. So sulfuric acid is made from a process called contact process, and the raw material is sulfur dioxide. How do we get sulfur dioxide? We get sulfur dioxide by reacting sulfur with oxygen, and then you can also get sulfur dioxide from the extraction process. We saw, like when you heat metal sulfide during extraction, you form sulfur dioxide. So this sulfur dioxide, instead of allowing it to go to the atmosphere, you can use it to prepare sulfuric acid. So just in brief, how this one is made, the sulfuric acid is gotten from sulfur dioxide. We have a process, sulfur dioxide combines with oxygen to form sulfur trioxide. And again, this reaction is exothermic, so it means it occurs with release of energy in form of heat. So it's normally carried out at low temperature. So this is how we represent the process, just like the other one. You have sulfur dioxide plus oxygen. When they react in presence of a catalyst, the catalyst that we use here is vanadium oxide, V2O5. You can see the pressure is a bit low, not like for the case of aluminium. And so we have that a low pressure, and then so there are things which keep on popping, and then the oxide. So when you mix that, you get sulfur trioxide. So after getting sulfur trioxide, this sulfur trioxide, when you combine it with water, it fumes a lot. It fumes to produce sulfuric acid fumes. So to prevent this, instead of dissolving sulfur trioxide in water, we reacted with sulfuric acid. We diluted in sulfuric acid to form oleum. There's a compound called oleum, and then after you have formed oleum, that's when now we react oleum with water to get a sulfuric acid. So the sulfur trioxide is not mixed directly with water, because when it mixes with water, it produces a lot of fumes, and these ones affect the environment. So the sulfur trioxide, SO3, after you have formed it from sulfur dioxide and water, we dissolve in sulfuric acid to form oleum. And then once you have formed oleum, you can react it with water to form sulfuric acid. So how do we explain the conditions? Just like the other one, we said because it's exothermic, we carry it out at low temperature, of 450 degrees, because this reaction is exothermic. To favor it according to Lachatlas principle, you need to ensure that you reduce the temperature. So the temperature has to be low according to the Lachatlas principle, but again not very low because of the kinetic factors. You need the reaction to proceed very fast. Now for the pressure, this is what we have said. You are starting with 3 moles, 2 plus 1, and you're ending up with 2. So it means this reaction occurs with a decrease in pressure. So you need to favor this reaction by trying to increase the pressure a bit. But again, we know maintaining high pressure could be expensive, so we try to get a compromise process. And then the other thing that we need to have here is a catalyst, and because these are gases, we normally use solid catalyst so that you can be able to speed up the process. So this is for aluminium, and so this is for ammonia and sulfur. So ammonia, we get it through Haber process. Sulfur, we get it through the contact process. So maybe that's what I can say for now. I can see we have remained 2 of us. What do we do? Can we maybe just continue tomorrow with the same number? Dennis and Kimta.
Yes. Maybe you can proceed from there tomorrow.
Tomorrow, the same number, hata wawili tutaendelea because nimeona some people are just here to slow us down. And I even see people asking for extension of the cut, and they're not even coming to class. So how do they expect us to move? Because I got discouraged on Monday. Yesterday, I also just got discouraged. I saw people are not coming. So today I decided we continue. So let's just continue even tomorrow, the same time.
Okay.
Yes. Asante.
Okay.
So wacha niwache hapo.
Same time.
Okay. Sorry?
That means we'll start at 8, I'm on 7.
You know, if munatakaje muniambie tu. If you want 7, you can start at 7. Or we can even start at 6:30 if you don't mind.
7 is appropriate, or even 6:30.
Wacha tuseme basi tuanze 6:30 tumalize by 8:30.
Okay.
Tomorrow, asanteni.
Sounds better.
Thank you. Yes. So tuanze 6:30 kesho.
Okay.
Sawa.
Okay, thank you. Have a good evening and thank you for persevering.
Okay, you too.
Good evening too. Dennis.
Yeah. Hello.
Je, kuna mtu anakuja class?
Kama
Ama
hawajisikii. So mimi huwa napost hapo kwa group karibu kila siku, naambia kuna class, lakini sioni wakiattend. Wanakuja
Mimi nilikuwa
mmoja.
na post mpaka nimekosa hope, yani unashindwa tu. So like you are forcing them and they don't want. Ama na sisi tuko wachache wenye tumeregister yule.
Hapana, watu ni wengi sana. Hiyo unit tuko we are more than 80 students. But those who are appearing for the classes are very few.
Na yule lecturer amesema max ya cut ataweka wewe.
Sijui unajua.
Nataka kuuliza lakini unajua mimi niliingia late. Nilikuwa nimeslake. Nimeingia kama mumeanza kupick.
Lakini si niliona ulikuwa on before utoke. Ulikuwa on before tuanze, alafu ukatoka tena. Nilikuwa hata nimejaribu kukutext na text message, nikaona haukuipata.
Okay. Siko. Usingeni text na WhatsApp.
Nitajaribu next time. Yes?
Kuna past papers ya nini?
Niko nazo.
Si utanitumia kwa inbox kwa WhatsApp.
Sawa.
Nisaidie kurefine.
Nitumie ni text na namba, unajua tu naona hapa admission number, unajua hapa hatuna namba.
Sawa, unajaiona namba yangu. Sawa, wacha nikuinbox basi.
Ah,
Acha nikusalamia WhatsApp, alafu utanitumia. Tashukuru.
haya.
Na unafanya physical chem?
Yes?
Unafanya ya physical chemistry?
Hapana. Na yenye nafanya ya chemistry ni na classical analysis and separation techniques. Sijui kama unafanya hiyo.
Hiyo bado mimi my friend sijafanya hapo.
Uko 2.1 ama ni 3.1? Hello?
Niko hapo tu. Niko hapo 2.2.
2.2. Oh, mimi ndio naanza. Mimi niko 1.1.
Na ukakujaje mbao wafanya hiyo mambo ya separation sijui what?
Niko 1.1, hizo ndio unit nimeregister. Unajua mimi nafanya second degree. Hii si ya first.
Oh.
Nilikuwa natulia. Kaona huko nje vyenye kumekaukana, nikaamua kufanya second degree. Sasa ndio nimeanza this term.
Sawa, basi all the best in your journey.
Okay, uko campus gani? Eldoret? Oh, mimi niko Meru. Niko Meru campus.
Na unajua hata huyu lecturer tumemingle na yeye mahali na lakini sijataka alijue. Sasa naona
Oh, hapo campus?
uliza maswali. Sitaka nitambue.
Hapo campus?
Kuna time tulifanya kazi na yeye kwa University of Eldoret.
Okay.
Sasa ananijua kabisa. Hata juzi nilikuwa na avoid hiyo mambo ya kutumia watu kwa email. Situmai communicate through that email. I think hata because wakati niliandika email hapa akanitumia. I think alijiuliza email si new.
Hata mimi huwa alinitumia hata mimi kwa email.
Ni Dean of School of Environmental Science kwa University of Eldoret.
Oh, mimi sasa sijui, unajua tu tumepatana hapa online tu hapo kwa WhatsApp sijui.
Hivyo ndio mimi nilikuwa nimemjua yeye. Sasa venye na kama anakuja huko kufunza part time ama tunaona hata mambo ya environmental tu. Yeye ni environmentalist by the way.
Nadhani akosangi hata lectures huko juu kuna siku anatuambianga sijui tuanze sijui kama ana push class ni kama anakuanga na maklasi zingine. Kama bado ni za online na hata sijui.
Labda zingine ya online ama physical. Huwa unos. Lakini chef sahi UAE unless UAE sahi watu wako long holiday mpaka September. Sasa unless part time na online.
Oh.
Mimi
degree sijui kama sitaienda holiday. Nafanya tuasem mpaka nimalize. Sitaki kuenda holiday. Sitaki kazi.
Utamaliza.
Sitaki kaa sana. Sitaki kusoma kukaa shule sana.
Utamaliza. Si 2.5 years.
Na hiyo ingine ya prac. Unafanya combination gani?
Nafanya maths chem.
Maths chem. Mimi nafanya biochem. Nafanya biochemistry.
Hiyo ni combination poa.
Wacha tuongee siku ingine. Ni text WhatsApp.
Have
Uko na
good night.
namba yako?
Sinachukua tu kwa
Okay. 92.